in this problem, we're going to try to find the limit of this sequence defined by n plus minus 1 to the power n over n minus 1 to the power n. Okay, in this case here, we have this minus 1 to the power n is changing between minus 1 and 1. So we can't decide. We need to find a way to get rid of it. Okay, and one of the keys is that this is a historic limit that one needs to know, because we're going to see what the result that we can get from here. So we can learn a lot from this limit here. So what we can do is we can study the even terms and the odd terms and see where they can go. So they must go to the same limit, otherwise it's divergent. So first we're gonna do a to n. Okay, in here we just switch n to n, and we have minus 1 to 2n over n minus 1 to 2n. Okay, here we have 2n plus 1 over 2n minus 1. I forgot the 2 here. So therefore we have this one here. So this sequence a to n is let's write it again. It's 2n plus 1 over 2n minus 1. It's behaving as 2n over 2n, which is 1. Okay, therefore we can see that the limit of a to n is 1 as n goes to infinity. Okay, so we don't stop here. We need to see the behavior of the odd terms. Okay, that's why we need to compute a to n plus 1. So here we have 2n plus 1. We just plug in 2n plus 1 in the original sequence. Okay, plus minus 1 to the power n plus 1 over n minus 1 to the power n to n plus 1. Here we're gonna have 2n plus 1, and this term here, it's gonna be negative. Okay, because it's minus 1. Okay, to an odd power, and here I forgot 2n plus 1. Sorry, it's 2n plus 1. So it's gonna be 2n plus 1. And what's this one here? It's gonna be minus 1, therefore it's gonna be plus 1. So therefore we have 2n over 2n plus 2. So when we see the behavior of this one here, okay, it's just like 2n over 2n, which is 1. Therefore the limit of a 2n plus 1 is just 1 as n goes to infinity. Okay, so we have these two results. This one here, this one, and this one. Okay, we can conclude that since the limit of a to n and the limit of a to n plus 1 is 1, the limit of our sequence is 1. Okay, so this is true, and it's true in general. Okay, so if we have a sequence such that the limit of the even number goes to L and the odd term goes to L, so here we have an goes to L as n goes to infinity. Okay, so we're gonna prove this one in general. This is a criterion sometimes when you have these ones here. So this is how you get rid of them. So you study the even and the odd and the terms, and they must have the same limit. Okay, so before we finish, let's give a counter example when we see that we can't conclude very quickly. So let's define an by minus 1 to the power n. Okay, this is a sequence that's minus 1, 1, 1, minus 1. It's alternating between minus 1 and 1. So if we want to apply this one here, so that means that if we have these two, we have this. If we don't have this one, therefore either one of them is different. Okay, Okay, so here we have a to n is minus 1 to the power 2n, which is 1, and a to n plus 1 is minus 1 to n plus 1, which is minus 1. So we have two different limits. The odd number, the even number, they converge to 1, and the odd to minus 1. Okay, therefore this is not convergent. Okay, so therefore remember this. Okay, this one here, when we have some kind of sequences that they have this alternating, some sequences, not series, sequences, when they have this one, this is how we get rid of them, by applying this criterion. We can prove it in theory. I'll prove it later, maybe next week. We're gonna see how to prove this one when you use the epsilon delta criterion, or we write the general term for a convergent sequence. Okay, anyways, so this shows that the limit of an is 1, okay, as n goes to infinity. Thank you very much.